As we jump into these more advanced conversion problems, the biggest piece of advice that I can give you is to be very, very specific with your labels when you're setting up your conversion factors. With this particular problem, we're asked to determine the number of ions, and that's super important. When you see ions, molecules, atoms, that should be a red flag that you're going to need to use Avogadro's number. In 2.12 moles of zinc phosphate. So the other big piece before we start our dimensional analysis is to correctly establish the formula for zinc phosphate. Just like the other problems, I'm going to start with what they gave us. So 2.12 moles and then zinc phosphate. I know I'm going to have to get rid of the moles of zinc phosphate. So in my conversion factor, I'm going to put it in the denominator. And we eventually want to go to phosphate ions. And we do know that from a formula, we can establish a mole-to-mole ratio between the different things in the formula, right? So here I'm thinking 1 mole of zinc phosphate, and then we have this subscript of 2, has 2 moles of phosphate. And that conversion factor, these numbers are directly from the formula. What's canceled? So we're done with moles of zinc phosphate. That's out of there. Now we got to get moles of phosphate to turn into phosphate ions. And we're going to do that by using Avogadro's number. So 1 mole of phosphate contains 6.02 times 10 to the 23rd phosphate ions. So this would cancel with this. Moles of phosphate is gone. And then we're just left with phosphate ions. Multiplying across the top, I don't have to worry about anything in the denominator here. I obtained 2.55 times 10 to the 24th phosphate ions. And I rounded it to 3 sig figs because of the 3 sig figs with our initial value here. Another problem about zinc phosphate, this time we're asked to solve for the number of oxygen atoms in a sample that has 6.89 grams of zinc. That's the piece of information I'm going to start with. And it's super important here to note that we're just talking about the zinc in the sample. Granted, the whole thing is zinc phosphate, but somehow they just got the mass of zinc. So whenever we're in grams, we should be thinking about heading towards moles. So I grabbed the value off of my periodic table. 1 mole of zinc contains 65.38 grams of zinc. And from there we can see that we already got rid of grams of zinc. Now we're in moles of zinc. And since we know the formula of zinc phosphate, Zn3PO42, we can relate the moles of zinc to zinc phosphate as a whole. That would be an option. But actually looking at this, I think it would be a little bit shorter to relate the moles of zinc. There's going to be 3 moles of zinc per every 8 moles of oxygen. So let's do that. Lots of options though. If you go a different route and get the same answer, then be confident about your approach. So here we have 3 moles of zinc and then the 3 coming from the formula. And I'm also going to grab an 8, 2 times 4, 8 moles of oxygen from that same formula. And just like our previous problem, they're asking us about individual things. So they're asking us about individual oxygen atoms. Being at the mole level, I need to use Avogadro's number to get rid of moles of oxygen and turn it into atoms of oxygen. Alrighty, so plugging all of this into my calculator, I got 1.69 times 10 to the 23rd oxygen atoms. Letter C is pretty challenging. They're asking us to calculate the total number of atoms in a 0.45 gram sample of zinc phosphate. So because they gave me the mass of zinc phosphate, the first thing I did was calculate the molar mass of zinc phosphate, the whole thing, and use that as a conversion factor to get to moles of zinc phosphate. Always think about heading towards moles first. Now I need to get rid of moles of zinc phosphate, so I put it in the denominator of my next conversion factor. But how am I going to calculate total atoms? So if I look at zinc phosphate as a whole, I know that 1 mole of zinc phosphate has Avogadro's number of zinc phosphate units. If it was covalent, I'd call it molecules. Let's do that. I'm going to put it in quotes. Not 100% correct to call it molecules, but I think it's a little bit easier to conceptualize than unit, right? So if we have that many zinc phosphate molecules, how many individual atoms are we dealing with then? So if we look at 1 molecule of zinc phosphate, we can kind of break it down. Or think about if you were going to use your molecular modeling kit to go ahead and build one unit of zinc phosphate. You would need to grab 3 atoms of zinc and 2 atoms of phosphorus and to complete your model you need 8 oxygen atoms. So altogether that equals 13. So 1 unit or 1 molecule of the zinc phosphate is going to have 13 individual atoms. So over here, for my last conversion factor, I can say 1, and again I'm using the quotes, 1 molecule of that zinc phosphate has 13 atoms. Let's look at how everything canceled or didn't cancel. So molecules of zinc phosphate will cancel with molecules of zinc phosphate, and I'm just left with atoms in the numerator, which is perfect. So plug this all into my calculator. I get 9.12 times 10 to the 21 atoms. In this problem, we're asked to determine how many water molecules are associated with 3.8 moles of sodium sulfate decahydrate. So For the purposes of this course, your hydrates are going to be associated with ionic compounds. So the first thing, like when you're doing the nomenclature of a hydrate, is to figure out the formula of that ionic compound. That works the same way. We got sodium, it's in group 1, so we'll do Na+. We got sulfate, that's one of our polyatomic ions, SO4 2-. I'm going to crisscross the charges, and that gives me Na2SO4. So I established the sodium sulfate part. Deca is one of our numerical prefixes that you might remember from our covalent nomenclature lessons. So deca means 10. So this salt is associated, it has 10 water molecules attached to it. And the way we write the hydrates is we always put a dot. It doesn't mean multiplied, it means attached. And then you're going to put how many, in this case 10, and then I'm going to write H2O. So Na2SO4, little dot in the middle, 10 H2O. How many water molecules? Dimensional analysis again. So we'll start with the 3.8 moles. I know it's a pain. You gotta write it out. You have to be specific, or else it's gonna create confusion. Half the battle with chemistry is staying organized, whether it be in the lab with your stockroom and your chemicals, or on paper with your calculations. So we have moles of sodium sulfate decahydrate. I want to get rid of that and get down to water. I can go mole to mole, moles of the compound as a whole to moles of water using the subscripts and the 10 out front here. So I'm going to say 1 mole of our sodium sulfate decahydrate has 10 moles of water. Excellent. So we've gotten rid of the moles of the sodium sulfate decahydrate. And now we just want to get to the level of water molecules. And molecules, we're thinking Avogadro's number, right? So I can put 1 mole of water on the bottom has 6.02 times 10 to the 23rd. Again, I want to be really specific. What am I talking about here? Water molecules. That way, moles of water is canceling with moles of water, and I'm just left with water molecules. So plug this all into your calculator, and I'm going to round it to 2 sig figs, giving me an answer of 2.3 times 10 to the 25th water molecules. To calculate the number of hydrogen atoms in a 2.86 gram sample of sodium sulfate decahydrate, we're going to need the molar mass of the hydrate. I want to go through that very briefly because I know hydrates are unfamiliar to a lot of students. The beginning part will be exactly the same as the process for calculating the molar mass of an ionic compound. So I'm going to do 2 sodiums. And then we have 1 sulfur. And then 4 oxygens. So to complete this, with the hydrates, I'm always thinking about the fact that, or I calculate ahead of time, that water has a mass of 18.02 grams per mole. I don't like to break down and start distributing the number out front of the water. Find it easier just to think, okay, I got 10 waters and I'll do 10 H2O in my little spreadsheet here. And that's going to mean 18.02 grams times 10. And then just add all that up. This time I got a total of 322.24 grams per mole for the hydrate. I started my problem with the 2.86 grams of sodium sulfate decahydrate that they told us we had in the given information. I used the molar mass that we just calculated to get rid of grams. And now I'm at moles of sodium sulfate dodecahydrate. I know I need to get rid of that, so I put it in the denominator of my next conversion factor. And we're asked to go to hydrogen atoms. And so looking at the formula for the sodium sulfate decahydrate, I'm noticing that we have 20 hydrogen atoms. So it's going to be the fact that we have 10 molecules of water and each individual molecule has 2 hydrogens. 10 times 2 is 20. So that's in 1 unit though. Right now I'm at the mole level. So I can say 1 mole of sodium sulfate decahydrate has 20 moles of hydrogen. And to get to atoms, I need to use Avogadro's number. So I'm going to do 1 mole of hydrogen in the denominator and Avogadro's number of hydrogen atoms in the numerator. So moles of sodium sulfate decahydrate will cancel moles of sodium sulfate decahydrate. Moles of hydrogen cancel moles of hydrogen, leaving us with just hydrogen atoms. 3 sig figs, so I got 1.07 times 10 to the 23rd hydrogen atoms.